Okay, so we're talking about the fundamental theorem of calculus. There's two parts of it, and I always joke that you have to get a little ways into Calc 2 before you talk about the fundamental theorem of calculus. You'd think that would be the beginning of it, but you had to get all the way to pre-calc before you talked about the fundamental theorem of algebra. So, what else is new? Fundamental theorem is, the first part is something that you're very comfortable with and familiar with. It's the idea of a definite integral, and it tells us that if we integrate over a particular interval, that all we have to do is substitute those bounds into our definite integral's antiderivative, and then simplify, and we have the result, whatever that is. Right? And we'll talk about what that means in a little while. All right? The second part is not as crystal clear, but it's profoundly important. You would think that it wouldn't be, especially with all that notation. It's like, oh, well, this must only be for the people who really, really like calculus. This is actually a way of redefining a function in terms of other variables. Right? So it's one of those things, unfortunately, where the payoff doesn't really happen until probably like halfway through Calc 3. So, I hate to do that. But there are a few topics where it's like, yeah, sit tight till Calc 3 and this will become perfectly clear why you do this. But it isn't until you learn about parametric equations, polar equations, and things like that, where something like the second fundamental theorem starts to solidify in your mind as something that's like critically important. Prior to that, it's like, well, yeah, we could do some kind of interesting problems with it, but it doesn't feel like it's absolutely necessary. All right? Definite integral is an area of a region. All right, that's really why we're after this particular topic, because what the definite integral over an interval gives you is the net area over that interval. All right, so the net area over an interval. Specifically bounded by the function and the x-axis or the y-axis, depending on how the function is organized. All right? But that's a lot to write, so I'm just going to leave it as the net area over an interval. And we'll discuss in more detail what that means specifically. All right? So a lot of like bits and pieces here. You can read the blurb. But we're going to kind of get into all those details. I mean, we're going to more than kind of. We're going to really get into those details as we move along. So I don't really feel the need to read that to you. The properties of definite integrals are really important. Not just as time savers, more so as just ways to generally understand what a definite integral is really telling us. Right, so we'll take a look at a few of them and see if we can conceptualize them. So the first one is saying on the interval of a to a, f of x dx is equal to 0, the integral. So what that's telling me is that I have two bounds, x equals, I don't know why. Like, why can't I just remember to put the pen on? X equals a to x equals a. All right, so what you have is some arbitrary function. I'll give an x and y axis. What it's saying, because we're talking about a net area, it's saying how much area is contained over the interval of a to a. So I'm starting at a and ending at a. All right. So what happens here is I've captured no area. All right, there was no movement off of A. So I didn't gain any area, whether it's positive or negative, because you can have negative areas. All right? And we'll talk about context in a little while, but that's really what it comes down to, is like if you haven't moved anywhere, how could you gain any area? All right? So it would make sense that if the bounds of integration are equivalent to one another, that you're looking at a case where no area would be contained. So I'd label this as A, but that if I were to create a line here, that would be the line x equals A. Right? Now here I'm saying that I'm going from x equals B to x equals A, specifically from B to A. All right? So I'll label that as x equals. I'm going to give an arbitrary function here. All right, so I'm going from B to A. All right, well, in the alphabet, A comes before B, so I'm going to label this as A here and B here. All right, so start thinking about just the geometry of the thing. All right, so if I were to draw a rectangle on this interval, somewhere, doesn't matter where, a single rectangle. All right, I'm thinking in terms of Riemann sums. When you're taking like all those little rectangles and squeezing them into an area and trying to use that to approximate the overall area within an interval. All right, there's a couple of things that come into play. There's two dimensions. We talked about this yesterday. One dimension would be the height, which would be y, or we could say f of x. The other dimension would be a horizontal distance. All right, so if I'm going from B to A, I'm going in that direction. Just to exaggerate the figure, I drew like a jumbo rectangle. All right, so f of x is the height. So I'll even accentuate that a little bit. But the dx is moving in the negative direction. And actually, I mean, this is a pretty wide interval, so let me amend that and make that a negative delta x, because I don't think anybody's looking at that and saying that's an instantaneous change. All right, so I'll try to be a little consistent with my diagram. All right, so what we're looking at here is as I go from B to A, so from B to A, I'm looking at an area equal to negative f of x times delta x. So if I went in the reverse direction, so if I went from A to B, I'm looking at an area where the f of x is still the same. Oh, don't need that. But delta x is now moving in the positive direction. All right, so I'll just draw another little rectangle in there to drive that point home. I'm going to go blue. Those give me score at home. Draw a little rectangle over here. Still has a height of f of x. But since I'm going from A to B, delta x is a positive movement. All right, it's a direction that's going to the right. And so therefore, what we get is the idea that depending on the direction that you're moving in, you're looking at a positive versus a negative area. All right? So what does that mean? It just means that if your bounds are not the way you want them, you can switch them around as long as you negate the area. All right? And since the integral represents the area, you just slap a negative symbol on the whole thing. All right? So that's a little weird one. Again, I think it falls in the category of most people are fine with, okay, it's a rule. I'll just memorize the rule. But I much prefer that you didn't just do that. All right. Something else to keep in mind, and this doesn't always work, but when it does, it could be a lifesaver. And I'll show you how to do this on the calculator in a little bit. Sometimes just try a numerical problem. Well, I don't know what the relationship would be if I switched the bounds. All right, well, make up a problem and switch the bounds. Oh, wow, that gave me a 2.5. When I switched them around, it gave me a negative 2.5. I strongly suspect that it's a negative relationship. You know, something like that. I mean, honestly, that's how I got through math too. Or at least the Regents. I didn't study for that. I get those Regents exams. Really stinks because I'm teaching a Regents class now. and I have to pretend that, you got to study like every night for like 27 hours. They're like, there isn't even that many hours in a day. I was like, I don't care. Make a time machine. Study for 27 hours every day. It's the only way you're going to pass. And then I just reflect back to when I was a student and the exams were harder. And I was like, study? Nah, I'm not doing that. I refuse. Wing it. That's the meaning of life. It generally does not work, so don't wing it. Anyway, additive interval property, I think that one probably doesn't really need much explanation, because if I have an interval going from A to B, if I split it up at some value along the way, then take the areas consistent with those two bounded regions and add them together, I'll get the total area. I could draw a picture, but I honestly don't think you necessarily would need that one. Constant multiple property. I've grown to like this one graphically, as opposed to back in the day where I would say, well, it's just a rule, get to know it, you'll be fine. Start off with like a simple example. And here I'm not even going to go with an arbitrary function. I'm going to go with a constant function. All right, so I'm going to call this f of x. All right, so some constant function f of x. I don't know what it is. Is it 1? Is it 20? It doesn't matter. All right, on the interval of a to b. Here's, well, let me not put it there. Here's a, and here's b. So let's say, let k equal 1/2. All right, so I'm taking half the value of the constant function. So k would now be, or k f of x, I cannot draw a line to save my life. All right, k times f of x would be right here. All right, so this area here appears to be, or at least the way I drew it, or attempted to draw it, it appears to be at least close to 1/2 of the original area. All right, if I'm talking about the bounded area between the function and the x-axis, you have this whole rectangle here. If k is equal to 1/2, I'm chopping the function in half, so I'm reducing its height consistently by 1/2, a factor of 1/2, then its area would necessarily be reduced by a factor of 1/2. All right, so that's all it's really saying. And the notation is the key to everything here, because this first part is telling you take all the y values and chop them in half. What this is telling you is that the resulting area, because that integral is saying area over an interval, will now be reduced by 1/2, assuming k is equal to 1/2. If k is 20, then each y value gets multiplied by a factor of 20. But that means that the overall area would be multiplied by a factor of 20. Okay. So that constant multiple rule takes on a lot more meaning now, in that it's not just a rule to memorize. It's like there's geometry behind it, and that's pretty cool. All right, the next one has to do with just sums and differences. So it's along the same lines. If you were to add two functions together, it's along the same lines as this one, where you're impacting the height of the function. So that's necessarily going to impact the area. So you're taking the sum of or difference of the two areas. I'm going to gloss over this one for now, because when we talk about the area between two functions, this one's going to come back big time, and I'm going to spend a little time with it then. All right. If f is integrable and non-negative on a to b, then it's telling us that its area would be non-negative. So that's just telling us that if a function is above the x-axis, then its area is going to be positive. If it's below the x-axis, its area is going to be negative. All right. And that has to do with the heights. Because if I'm moving from left to right, so from a to b, so make that assumption, we're going from a to b, or a to b, the x value is moving in the positive direction. If I'm above the x-axis, then my y values are positive. Positive times positive is positive. If I'm below the x-axis, then I have positive times negative, which would give me a negative. All right. So it's all the geometry of it. And then the size relationships are steady also. So if one function is physically above another, it's going to contain more area. Right? If it's below, it'll contain less.